Hello everyone. In this video we are going to use Excel to help us do a one-sample hypothesis testing when we are doing matched pairs. Okay, so remember matched pairs are when we have like the same individual or the same thing and we kind of measure it like two times and we take the difference in those measurements and then we are able to do our one sample hypothesis testing on the difference. So let's look at this study. So it says, in this study, the weights of young female anorexia patients was recorded before and after family therapy. So the directions performed an appropriate significant test at the alpha level of 0.05 to determine whether or not the weight gain was statistically significant. Okay, so let's grab our data first. And we see we have this therapy pre-weight and we have this therapy post-weight. Then we have the post minus the pre. So let's go ahead and copy this data over and let's put it into our Excel file. Okay, as we can see, a whole lot of these individuals, they had higher weights after their therapy. So let's look at that pre and post. But there were some who lost weight during therapy. And like, that's kind of like realistic stuff. And so we want to see, it's like, on average, did we see weight gain? And that's what we really want to test. So since that's what we want to do, we want to select the null and alternative hypothesis. And so when we are testing this match pairs, almost always we're testing it as compared to 0. It's kind of this default option. And we want to test, up here it says, to determine whether or not significant weight gain was, that the weight gain was statistically significant. Okay, so we're looking for weight gain, which means that this mu d is going to be greater than 0 because we want the post minus the pre to be bigger than 0 because that means that we would have weight gain. So this is our null and our alternative. And then also remember, let's just type it in somewhere, that our alpha level is equal to 0.05. Okay, so now we need to compute our test statistic. And our test statistic that we are going to be interested in is really simple. Let's go ahead and just take a look at the equation. So it's this t equals x bar d divided by the standard error of the sample divided by the square root of n. Or we can use the standard error divided by x bar. And let's just go ahead and do that real quick. So the first thing that we need to do is we need to find the average of the differences. So let's go ahead and highlight our pre minus post. Let's pull up our real stats package and let's do our descriptive statistics and normality. Click OK. We need this first box checked because I have a column heading here. I want my descriptive statistics. I don't need any Shapiro-Wilks or plot stuff. And I'm going to put my output range as just this E column. And I'll go ahead and click OK. And here we have our descriptive statistics of our post minus pre. We have our mean, we've got our standard error, we've got all the pieces that we need. So in order to do this, let's go ahead and use this equation over here. So we're going to say that t equals, and I'm going to put an equal sign here, and I'm going to say x bar. And now technically, like, they have x bar d. This is our x bar d. Technically, they really probably should have done a minus 0 because they're supposed to minus what the hypothesized difference was. Most of the time it is a 0, but we're just going to put it in for good measure. Divided by, and we could do it like how they did, take the standard deviation divided by the square root of the sample size, or real stats already did it for us. We just divide by the standard error. And we go ahead and click enter, and the answer was that 4.089, and we have that 4.089. So we got our t-value. So now that we've got our test statistic, now we need to compute our p-value. So now remember, in order to compute our p-value, we need a little bit of code. So we're going to type in p-value. And in order to do this, we need to figure out how many standard deviations away from the mean this is, and like well, we already know the number of standard deviations. It's like a little over 4, but we need to figure out the probability of that. Let me show you real quick with just a little drawing. Okay, let's bring this over real quick. Let me draw. Okay, so remember, is it not going to let me draw? Okay, here we go. So remember, we've got our kind of like normal distribution. Here's the center, and the center was at 0. And we found that our particular t was like 4 standard deviations away. So we've got kind of like 1 standard deviation there, 2 standard deviations, 3 standard deviations, and 4 standard deviations. So this is kind of where our x bar d landed. Like we're really far away from the mean. And the p-value then is going to be the area under the curve. Like if our curve actually extended out that far, let's kind of keep on going. Great. Our p-value is kind of this area under the curve right here. It's really small. There's not a lot going on, and we need to figure out how to get this area. Okay, with that being said, let's kind of come back here to how we get our p-value. So we're going to say equals t dot dist. We need our x value here, and that represents the t that we calculated. There's our t. We need our degrees of freedom, which is, remember, our count minus 1, comma, and then it asks for cumulative. And we do want the cumulative, so we want to say true. I want to hit enter. Now, notice here that our p-value gave us a value almost equal to 1. But here, when we look at our graphic, let's see if I can get it to come over. We said that we were supposed to have a really, really small p-value. So remember, when we calculate out this p-value here in Excel, when we ask for the cumulative, just like it did in our binomial or other ways, is that it gives us the area from our critical point and to the left. Notice how that's like almost 1. That's almost all of the area under the curve. So in order to get the correct value, we need to take the complement of this, which is 1 minus this t dot dist. And if we hit enter, we get 0.00043. And if we come and look at our answer, we get 0.00043. And notice here it says compute the p-value using a student t distribution with 16 degrees of freedom. Since the alternative hypothesis of greater than form, the p-value is equal to the area of the right tail. And when we come and look here, that's what we got, the area of the right tail. Okay, last question. So it says interpret the results. And we've got that the p-value provides strong evidence against the null hypothesis, or that we're going to reject this null hypothesis and claim instead that the true difference is greater than 0, or that the therapy helps these patients gain weight at a significant level. The only other thing that we could do here, and this question doesn't ask for it, and so we're not going to do it, but we could also provide a confidence interval, and it is the exact same way that we've been doing our other intervals. So you can go look at your equations for how to create your confidence interval for this one. Okay, that's it. Good luck on doing your matched pair testing.